Hey everybody, this is Larry. This is me going over Q4 of the recent Leetcode bi-weekly contest, delivering boxes from storage to ports. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. It was really hard. That's what I thought about this problem. So usually my format is that especially for contest problems, I explain the solution and the algorithm and maybe a little bit about my thought process, and then I give you the video. You could watch the video afterwards, right? Of me solving it live during the contest. So two things. One is I did not solve this during the contest, and two is that this is a pretty hard problem. Not in its components, but it's just that you need to put 3 or 4 tricky parts together into one problem, into one solution, and that's the part that I didn't solve during the contest. And in fact, I'll have a link below on the contest video, and you can watch me try to solve it during the contest. I couldn't solve it during the contest, and I spent an additional hour just getting it right. And actually, to be honest, I tried explaining this problem, the explanation from scratch, and that video ran about an hour and a half of just explanation, going step by step. So an hour and a half is a long time to spend on a problem, on a video of a problem, not even just solving it, right? So what I'm going to do here is that I'm going to say that again, which I said a few times already. This is a hard problem. Don't feel bad if you don't. Excuse me. Don't feel bad if you're unable to get it. That's one. I didn't get it. I'm not feeling that bad. Two is that, okay, here's a list of things that I recommend you practicing. And if you're unable to solve this problem, practice those things, and then you have to put them together. And even me, like I don't know, not to be bragging, but like you're watching my video, right? And I'm still not able to solve it during the contest. But I am here to explain it to you the best way that I can. And let me know what you think. I know that this is a really long intro, and this is a really weird intro for 2 minutes, but I just want you to understand that this is not an easy problem. So these are the things that you need to understand about this problem first, right? One is dynamic programming. This is a dynamic programming problem. This is a dynamic programming solution. So you have to be pretty familiar with dynamic programming. And more specifically, there are a couple of different types. One is you have to be familiar with prefix sum. Prefix sum by itself comes up in random places, and you have to be able to pull it out to figure it out to solve this problem. You might not need to. You could get away with other prefix sum E stuff, like some people have done segment trees and something like that. But I would say prefix sum. So that's one. Two is shortest path in a DAG. That's a dynamic programming solution. There's a problem with a dynamic programming solution. The canonical way is n square. If those words don't mean anything to you, find another problem that lets you solve that problem. Hopefully, either join me on Discord, or hopefully someone will put a link to some problems that are related to that, and practice those problems first, because you need to know that as well. And once you have those things, another thing that you need to learn, already have good understanding of, is sliding windows. Sliding windows in itself is 2 pointers, and it's okay. It's not bad. And if you are able to have a good, deep understanding of it, that'll help you solve this problem. I mean, you need it for this problem. I know that some solution also recommends monoQ and stuff like that. Actually, that surprisingly is not necessary. You may need to use that to solve it in O of n times in linear time if you really want to get the most efficient way. But I would argue that that's not the most interesting part of that problem. Maybe you could figure it out. But using a heap or some kind of heap-like algorithm which I'll show you below, you should be able to solve this problem in n log n, which is not optimal, but it's fast enough, and you already got for a lot of different hard parts, right? So basically, that's my disclaimer. So if you are not super familiar with each of those algorithms that I point out, go back and work on those. It makes, like if you're just gonna, like this problem is not a good problem to solve without a better understanding of those algorithms. Okay. Now, 5 minutes in, let's get started. Okay. So all that being said, let's go over. So I prepare not the final solution. We'll solve it together, but I'm going to start from the n squared solution. So this is my n squared solution. It works for most small n's, played around with it and stuff like that. The tricky thing is, notice that the number of boxes is n, which could go up to 10 to the 5th. And max boxes is n to the 5th, and max rate is n to the 5th, right? So that if max rate is 10 to the 5th, max boxes is 10 to the 5th, and all the rates are 1, you're going to become an n squared algorithm. So that's basically not what we want. But looking at this code, this is the way to do it in n squared dynamic programming. And the reason why we're starting from here, and this is how you find the shortest path between the shortest path in a DAG using dynamic programming. And the reason why we're starting from here is, from here we will do the optimization to get it down to n log n time, which is fast enough, and then with some hints, hopefully, to get you to O of n. Okay, so sliding window is the first thing that we're going to talk about with respect to this problem. I'm not going to go too deeply on how sliding windows work. Sometimes I do, sometimes I don't, but for this problem I just don't have time because it is a hard problem. So yeah, the sliding window is that, okay, let's look at this 3-7, which is port 3, has a 7 rate, say. Let's say that with one trip, or one trip has a different meaning here, but with one departure, say, with one departure, you're able to visit, this node, and this node, all in one group, right? Then now, when you process the next object, well, the two things that happens, right? One is that, well, now we extend this to the right, because now from here, you're able to look at the solution backward to be like, okay, now we have to consider 3-1 going to 3-7 as well as all the other stuff that we're already convincing, right? And the reason why we're using sliding window is that this is the only way to use these overlapping solutions, so that we are able to calculate this in really fast time. Otherwise, if you do another loop like I do here in the code, that's going to be n squared, and we're trying to get it faster than that, right? And let's say that we're able to get the min. If we're able to get the min of these segments in log n time, then that's enough for us to get it in n log n as we go left to right, right? And the two things that happen when we process the 3-1 here in this node, and let me make the font bigger. One is that we add this segment, right? I mean, that seems pretty straightforward. You can, from 3-1 going backwards, you have to connect to 3-7. Otherwise, I mean, you may be too heavy and not go that far, but you have to at least start in that consideration. And then the other thing is that, well, now let's say you added this segment or this box, and now it's too heavy or too many boxes. Well, now you have to remove boxes, and you only remove it from the front until it all is satisfied, right? So that's basically the invariant that we're trying to accomplish. The invariant here is that within these segments, the number of boxes is less than the max boxes, and sum of the rates is less than max rate, right? And every time we move that sliding window, that holds true. So if you have a good understanding of sliding window, this is actually not that bad to understand. I mean, you have to put it together, and that's the hard part, but right? Okay, so now here, from here, we ask ourselves, okay, if we're able to do one departure and we're able to go anywhere, where would we go, right? Well, here we have all varying costs. And the answer is, well, we take the min of everything inside, and then we just go there, right? It's kind of like a greedy kind of way, but you basically take the min inside that segment and then go there. So that's basically the idea behind this dynamic programming, but there's one more piece. If you recall, okay, we talked a little bit about prefix sum. I'm going to come right back to it, but for now, we're going to talk about one more thing about calculating the delta, right? Calculating the, this segment, changing to this segment. Okay, number of boxes is easy because it's just you add one box or you subtract one box depending on how you move the 2 pointers. If you familiar with sliding windows, that's obvious. For the weights, same thing, right? As boxes come off, you subtract the weight. As boxes come on, you add the weight. Also, very basic sliding window situation. But then the problem is that, well, the costs are not the same necessarily, right? Okay, actually in this case it is. But let's say we're here, and now we're considering the 4, 4, and we're considering here, right? Well, the cost, so the thing is that if you're here, and and this is me just reading from the problem, so feel free to read the problem again to make sure you understand the rules of the problem, because this is already a very long video. But here, going here, let's say we want to group these together into one round trip, right? Well, what's the cost of that? Well, the cost of that is just, you have one trip for departure, you have one trip to come back, and then you have one more trip to go from 4 to 3 or 3 to 4. It doesn't really matter as long as because it's symmetric, right? And in this case, so that's one more, so total is 3. Similarly, here, if you just look at these segment, then the answer is still going to be 3 because the 3 and the 3 are so forth, right? But then the problem is that, okay, if you look at the everything inside here, let's just say we keep track of what's inside, right? From here, at least from the distance of the 3, right? So here from 3, the minimal cost would be 0. We could add 2 back later. I mean, I think that's just going and coming back. So the 2 is consistent, so we don't have to worry about it for now. And then from the 3, 7, it's still 0 because it's the same as the other 3. This is 0 as well, and this is 0 as well, right? But now, if you look at the 4, I mean, this is kind of not a great example, I will admit, because everything should be. Let's just pretend for a second that this is 2. Then you have 1 because now you have to go from the departure point, go to 2, go to 3, and then 3 again. But then you don't have to move, and then come back. So it takes 1 here, right? I'm gonna also change this to 2 just for clarity, so that you'll see in a second. But now, if you go to 4, if you just very naively look at it, 4 will be 0. Because again, this is the same thing. You start from the departure point, you go to 4, you come right back. So there's only 2 trips. Again, we just ignore the 2 for now, and 0. Here, this is 1 as we said, because you have to go from the departure point to 3 to 4 to and back. So there's that 1 trip in the middle. Same thing here is 1. This is 2, and this drop off we said, so we could just ignore it. But and that's the tricky part about this, right? Is that, well, actually everything inside here is not the same as everything that's inside here. This changes as you add more numbers. But as it turns out, this is where prefix sum comes into play. This is a long wrap. Give me a second. But yeah, so this is where prefix sum comes into play, right? So that now, having this, you can actually pre-calculate everything counting from the very end. So let me type this out. So yeah, so for example here 5, so let's say this is 0, this is 1 because if we were to put these grouped together, we have to go from 0, or we have to go from the start, go to 1, go to 5, and then 0, so there's only 1. Again, this is 2, this is 3, this is 3, this is 4, this is 4, this is 4, this is 4, right? So basically the idea here now is that we don't need to, we could store different things in here. We want to be able to store things inside here that doesn't change. And the invariant of this distance metric is that it doesn't have to change anymore. Right now, instead of storing 0, 0, 1, 1, we could just store 3, 3, 4, 4. Oops. And here again is 4, 3, 3, 2, where now, and this is hopefully familiar to you, you're familiar with prefix sum, is that now you can see that all we have to do is just get the min of what's inside. I mean, well, I guess this includes the 2 for starting its own, and then we just have to subtract the prefix. I mean, in this case, it's the suffix, but suffix sum, I guess, is kind of a different thing. But right, so now, because here we subtract basically the delta from here, right? So that's basically all you need to solve this problem. I know that this is very tricky and it's very hard, and now I'm going to start programming it for you. So this part may be a little bit slower because I am trying to do this live a little bit. Now, because I wrote this another way when I first solved it, but now I think with this, I feel like it's great. It is easier to understand piece by piece by piece and not just assume some greedy algorithm or some those kind of things. I think when you're able to understand the components to its parts, then you're able to, reproduce how to solve it in the future, right? If you just memorize solutions, it's going to be tough to solve similar but not exactly the same problems. So okay, now we want to create a suffix sum. So I usually write it kind of funky, so bear with me, but yeah. Okay, let's just do suffix index is equal to n minus 1. While suffix index is greater than 0, maybe 1. Yeah, what we see? Oh, and this should be this times n plus 1. So yeah, so suffix of suffix index. I guess actually this is n minus 2, so that we could do this is equal to suffix of the suffix index plus 1 plus the whether they're the same, right? Because here, if they're different, then we have to add 1 to the suffix array. So oops, what's it called? Boxes suffix index of the port, which is 0, is not equal to. So something like that, right? Reference, and then suffix index minus 1. Actually, this could go to 0. And let's just do a quick print to make sure that I don't have a typo. Okay. So this looks okay. Yeah. Okay. So then now that we have the suffix array, and at least on first glance it looks okay. Now we're going to refactor our n squared dp. So now we want to rewrite it as a starting sliding window from left to right. So let's just rename some of these things. Sometimes I get it confused. Left is equal to 0 as well. We could just start over. Okay, let's go. So now we add a box to the and I guess the other thing is that, okay, how do you store this structure, right? Well, for me, you could actually, there are a couple of ways to do it. A min heap is actually good enough as well, as long as you make sure that when you remove a number, you don't use it in the future. There are a couple of ways to do that, but it's a little bit messy, so I'm not going to do that for now. I'm going to use in Python something called sorted list. And again, if you're really good with mono queues, you can actually use mono queues right now. Yeah, you're able to use mono queue. You're able to use the mono queue. But see if you are able to figure that out. I also have a tutorial on mono queues, so if you want to watch that, I think I did a good job, a reasonable job of explaining it. Let me know what you think. But we don't need the mono queue to. At least I'm not going to explain the mono queue portion. I mean, it's a good exercise of self after you figure out all the other pieces. I think these other pieces are more important to put together, right? Okay, so like now we add in the right. So let's start with, weight is equal to 0, number of boxes is equal to 0, and yeah. So now weight, well, we add in this weight, so the weight is 1. Yeah, the number of boxes we increment, that's just because we now add right box to the segment, I call it, maybe to the sliding window, so window maybe. Okay, there we go. And now while number of boxes is greater than max boxes, or weight is greater than max weight. So basically now our window is too big and we have to make it smaller, right? So we subtract boxes sub left of 1, number of boxes minus 1, and then we move left plus 1, right? So okay, so this part, it is very elementary sliding window. Hopefully this is understandable, because now we're going to have to incorporate the other parts. I think this part is okay if you, or should be okay if you're practicing sliding window. Okay. And then the question is, okay, what happens when we add, right? When we add, we just move we move right to here. So actually we're already covered. Suffix sub right should already give us the answer. So, dp of some answer, let's just say right, is equal to some element, something here. Let's just write something plus, or sorry, minus suffix of the right, maybe off by 1, but basically what it's doing here is that it takes the min element inside here, and then we subtract it from here, right? And then we have to add it to 2, I think. The 2 being that, you just have to go out and then you have to come back in, right? So that's just part of the problem definition. This is assuming 1 round trip. So yeah. So how do we do the summing minimum? Okay, so this is where we have sorted list comes into play. As I said, you could have maybe used mono queue or in C++ or even Java, maybe you use a set or tree map or something like that. But basically, I just wanted to get something that lets me get the min as we roll that sliding window. And I like sorted list for that reason, because I don't have to worry about anything weird. Yeah. So basically, okay. So let's say we added a new number, right? Well, that means that we just basically added this to the list. So that's actually pretty straightforward, right? So hopefully this is right, because it looks silly if it's not. But we add suffix of right. Yeah. We add suffix of right because I was thinking about making it 0, but then I remember that we will subtract it later, so it'll become 0. It's fine. But yeah, so it adds suffix it adds this to a list, and then now it has to remove this segment, which is this suffix, right? So now we just go sorted list dot remove suffix sub left. And then now minimum is just the sorted list, the first element of the sorted list. So that's pretty much it, except for getting the right answer would be nice. But So maybe I have something I'm missing. Hang on, let me print it out real quick. Why is this two? That's a little awkward. I mean, this part it may be just because I'm off by 1. Oh yeah, because right is 0, so this is actually +1. Oh, I'm just being silly. I mean, this part is still right, but then now we have to get so this is the cost from here. Okay, I'm just being silly. So this is the cost from here, right? But we also have to get the cost from this point to the from the beginning, right? So that's basically the rest of this problem is okay. Yeah. So basically, what I forgot, not we. I mean, it's always we when I get in trouble, right? So what I forgot was that when we put on D here, when we put things here, let's say let's actually say in English so that we can make sure that we get the off by 1s correctly, is that inclusively, let's say, we already took care of all these, well, we'll take care of all these later, but right here, we want to find the beginning of this round trip in the shortest cost, right? And that is, if we start the round trip here, then it is 3, again, minus 3 because of the prefix sum, plus dp of let's see, 0, 1, 2, 3, 4, right? Because this is, and dp sub 4 is of course the best answer that's right here, right? Here is the same thing, it's minus 3 plus dp sub 3. This is also minus 3 plus, well, the minus 3 gets factored in later, but this is dp sub 2, so actually let's remove the minus 3. Of course, everything is a little bit misaligned now, or a lot misaligned, but you get the idea, right? So that if you connect, let's say this 4 plus dp of 2 is, what does that mean exactly? It means that, okay, this is 1 round trip. It will cost 2 because it goes from the root node or whatever the beginning to 3 to 2 to 3 and then back. So it'll cost 4 plus 3, so it'll cost 1 plus the dp sub 2, which is the rest of the journey, right? So okay, so with that in mind, that should be an easy fix. This is plus dp sub y minus 1 because we're adding the right box, and actually now dp is off by 1 because we padded with the no object, so let's do that. And we also have to make sure we remove that as well, and let's give it a go. Ooh, 1 time error. Oh, and I forgot that this should be y plus 1. Because again, when this is 0, we actually want to populate the first element. And there you go. Right answer, let's give it a quick submit. Be awkward if it's wrong. Yeah, okay, cool. Whew. So this was a very long explanation video. I mean, I did some implementation as well, but this is a very hard problem. Maybe on a better day, I'm able to get it. Today, I'm not. I usually will have a link, or I usually have the video like right afterwards of me solving it during the contest. But to be frank, it's a little long. It's a little boring. There'll be a link below to the contest video. If you really want to watch me solve it, that's fine, and you can watch that, but I don't want to upload it again. But yeah, again, this is a really hard problem, especially if you are not as familiar with every component. So my first iteration of this video was 1.5 hours, and it's just way too long to learn so much. So hopefully this is a short version, and let me know what you think. Hit the like button, hit the subscribe button, join me on Discord. Ask me any questions because this is hard. And I will see y'all another problem. Bye-bye.